Okay, in this lecture, we're going to cover the next part of our section 12.3 material on optimization. And in these next few examples, we're going to consider some applied optimization problems where we're finding the maximum or minimum value of some quantity that's not just an arbitrary function over an interval, but has some physical or financial interpretation. So let's start with an example from business. So here, let's say that a company manufactures beach balls that sell wholesale for $75 per 100 beach balls. And the total cost in dollars of making X 100 beach balls is C of X equals 5X squared minus 20X plus 12. And we're told to assume that the company can sell all of the beach balls that it makes. So they can manufacture as many as they want, and they're guaranteed they can sell all of them. So how many beach balls should be made in order to maximize the profit? So here we know that profit is given by revenue minus cost, and we're given the cost function. So let's start by finding our revenue function. So here our revenue function, let's call it R of X, is equal to, well, we were told they sell wholesale for $75 per 100. And since X is being measured in hundreds, we can have R of X as 75 times X, where X is the number of 100 beach balls manufactured and sold. And we've already got the cost function C of X as 5X squared minus 20X plus 12. So our profit function, P of X, we know is defined as revenue, R of X, minus cost, which is C of X. So our profit function, P of X, is equal to 75X minus the cost function, which was 5X squared minus 20X plus 12, or simplifying, P of X is negative 5X squared plus 95X minus 12, where X, the number of 100 manufactured, must be non-negative, since we can't manufacture a negative number of beach balls. So we're interested in maximizing this function. So there's a couple of ways to do it. One way would be to find critical values of this function and make use of the first or second derivative test. So here, our derivative, P prime of X, would be negative 10X plus 95. And this derivative is defined everywhere, so the only critical values we would have are values that would make this derivative 0. So solving for X, we would have 10X is equal to 95. And so X is equal to 95 over 10, or 9.5. But remember, this was being measured in hundreds. So we would say 950 for this value. Now the question is, okay, well, that is a critical value. Does that value maximize profit or minimize profit? So to answer that question, we can make use of the first or second derivative test. And here, the second derivative test is pretty straightforward. If we look at P double prime of X, its value is negative 10, which is certainly less than 0, which means that our function is concave downward everywhere. Therefore, at our critical value, our function is concave down, and that critical value is giving us a local maximum. So we have a maximum profit if selling manufacturing and selling 950 beach balls. All right. Now, another way that we could have tackled this problem is by recognizing that our profit function, p of x, is a quadratic whose x squared coefficient is negative. So that means the graph of this function is a parabola opening downward. So of course the critical value that we find is a maximum corresponding to the vertex. So if we recall from chapter 3, the vertex occurs at x equals negative b over 2a. Well, for this quadratic, we would have negative 95 divided by 2a is negative 10. So 95 over 10, or 9.500, the same value that we found using the derivative. So let's look at another one, maybe a little more complicated. So in this next problem, we're told that an open box is to be made by cutting a square from each corner of a 3-foot by 8-foot piece of cardboard and then folding up the sides. So the question is, what size square should be cut from each corner in order to produce a box of maximum volume? So for these sort of problems, it typically helps to sketch a figure to visualize what exactly you're doing for this problem. So here we're told that we have a rectangular piece of cardboard which measures 3 feet by 8 feet. And we're told that we're cutting squares from each corner. So to visualize this, maybe we can extend these little lines where we're cutting our squares from each corner, and then we're going to fold up the sides. So after we cut out these corners, these sides that we're left with, these little flaps on each side, will be folded upward, and we will have an open rectangular box. Something that looks like the following. All right. And we want to know, well, what size square should we cut from each corner to get the largest box, the maximum volume? So our unknown quantity, the size of the squares that we're cutting from the corner, let's call x. So since this is a square that we're cutting out of the corner, each side has the same length. Let's call it x feet. So the remaining length for the side of our box, well, the total length along the bottom edge was 8 feet, and we've cut off x feet from both sides. So we would have 8 minus 2 times x feet. Or for these other two sides, well, the total length along that side was 3 feet. We cut x from each corner. So we've got 3 minus 2x. So here, the dimensions of our box are going to be 3 minus 2x. This longer side will be 8 minus 2x. And then the height of our box will be the length of one of these squares that we've cut out. All right. So let's see what the volume of this box would be in terms of x. So after we draw our picture and maybe label some variables, the next step in these optimization problems is to ask ourselves, well, what are we trying to optimize? And in this case, the problem asks us to maximize volume. So we want to introduce a function for volume. So here I'll call it V for volume, and the volume of a rectangular box would be the length, which is 8 minus 2x, by the width, which is 3 minus 2x, by the height, which was x. Or expanding and simplifying, we have V is, expanding here, we would have 8 times 3 is 24, minus 16x minus 6x gives us negative 22x, and then plus a 4x squared, which is then all multiplied by x. So our volume function is 24x minus 22x squared plus 4x cubed. Now we have to ask ourselves for most of these problems if there's any restriction on the values of x. Now we know here in order to form a box, well, we have to cut some square from the corner. We can't just fold this up as it is, so the value of x must be positive. And then let's think about the maximum possible value of x. So we know that the shorter of our two sides was this side of length 3. So the value of x can't make the width of our box, which was 3 minus 2x, negative. We have to have a width of our box. We can't cut more than is there. So 3 minus 2x has to be positive, which means 3 is greater than 2x, or x has to be less than 3 halves. So we can cut anywhere from 0 feet to 3 halves feet from the side, or from these corners. So here we have a continuous function over some closed interval, and we know therefore it has an absolute maximum and minimum value over that interval. So to find that value, let's see if we can determine the critical values of our function. So if we look at the derivative v prime, we have 24 minus 44x plus 12x squared, which is defined everywhere. So the only critical values we would have are if this derivative is 0. And if we divide through by 4, we have 6 minus 11x plus 3x squared is 0. And this can be factored as 3x minus 2 times x minus 3 is 0. So we have two critical values. Either x is 2/3 or x is 3. But recall the largest value of x was 3 halves, or 1.5. So we cannot have x equal to 3. Our only critical value is x equals to 2/3. And then the last part of this problem is to make sure that that yields a maximum volume rather than a minimum volume. So there's a couple of ways we could do it. We could make use of the first or the second derivative test. Here I might use the first derivative test. So if we're looking at the interval from 0 to 3 halves, 2/3 would be within that interval. And for values of x that are less than 2/3, so let's say maybe 1/3, our derivative is positive. Whereas if we take a value of x that is between 2/3 and 3 halves, maybe 1, if we substitute into our derivative v prime, we get a negative value. So the first derivative test says, since we're changing from a positive to a negative at 2/3, we have a local maximum at that point. However, the critical point theorem says, well, that was the only critical value within this interval, so it must be an absolute maximum. So in order to answer our question, or in the way that it was phrased, we were asked what size square should be cut from each corner in order to produce a box of maximum value. Well, we should cut a square of side length 2/3 feet, or 2/3 of a foot. Well, a foot is 12 inches, so 2/3 of that would be 8 inches. So we'll cut little 8 by 8 inch squares out from each corner, fold up the box, and that would yield the box of largest possible volume. So let's look at some other ones. In this next example, we've got a somewhat similar problem. We're told a company wishes to manufacture a rectangular box with a volume of 36 cubic feet that is open on top and is twice as long as it is wide. So we want to find the dimensions of the box produced from the minimum amount of material. So if we're producing a box, we know how large we want it, but we want to use the least amount of material. What should we do? So as with our last example, let's maybe start by visualizing our box. So we have some open topped box. So to indicate that it's open on top, maybe I'll put little lines across the top to denote that it's does not have a top on it. And we're told here that the length is twice the width. It's twice as long as it is wide. So if we label our width x, that means that the length would be double that value, 2x. And we don't know what the height of this box is. Let's call it y. So the height throughout is some value y. Now we're told that the volume of this box must equal 36 cubic feet. So let's consider an expression for volume. The volume of a rectangular box would be the length, which is 2x, times the width, which is x, times the height, which is y. And we're told that that value needs to be 36. So in other words, 2 times x squared times y is equal to 36. Now let's ask ourselves what we're trying to optimize. So here we're trying, or the problem says we want to use the minimum amount of material. So we want to minimize the surface area of this box. So let's find a function for surface area. We'll call it SA. So the surface area of this box, well, let's add up the area of all of our sides. So starting with the bottom of our box, well, we have a rectangle of side lengths x and 2x. So taking the product to get our area, we would have 2x squared. And then there is no top to the box. We just have the bottom. So now let's think about the area of the 4 sides. So for one of these sides, let's say the front part of our box, we have this rectangle with side lengths x and y. And then the area, of course, of the back side of our box would have to be equal to that value, x times y. So we have 2x times y for the area of the front and the back of the box. And then for the left and right hand sides, well, we have a rectangle of side lengths 2x and y. But that is the area of, say, just the right hand side. We know that's going to equal the area of this left hand side. We would have a 2x by our height y. So to get the left and right hand sides together, we would take 2 times 2xy. So simplifying a little bit, we have the surface area is 2x squared plus 2xy plus 4xy, or the surface area is 2x squared plus 6xy. Now notice that this surface area function involves the variables x and y. And we only know how to maximize or minimize a function of a single variable x. So in order to simplify this down to a single variable, we're going to go back to our volume constraint. We were told the volume must be 36, and we found the volume to be 2x squared times y is 36. So I can solve this equation for y in terms of x. If I divide both sides by 2x squared, I get y is 18 divided by x squared. So taking that expression and substituting into our surface area function, we have 2x squared plus 6x times y, which has to be 18 over x squared. So simplifying a bit further, our function for surface area is 2x squared plus 18 times 6 is 108, and then our x divided by x squared leaves us with division by x. Or if we prefer, 2x squared plus 108x to the negative first. So now we ask ourselves, well, to minimize this surface area, we're looking for a minimum of this function. So let's start by finding our critical values. So taking the derivative of this surface area function, we have 4x minus 108x to the negative 2, or divided by x squared. And this derivative is defined as x as long as x is non-zero. And we know x can't be 0, otherwise we would have a box of 0 width and 0 length. So the only critical values we have would be values which make this derivative 0. So we have 4x is equal to 108 over x squared, or multiplying both sides by x squared, we have 4x cubed is 108, or dividing by 4, x cubed is 27, and so taking the cubed root, x would have to be 3. Now again, the question is the same. How do we know that this value of 3 yields a minimum rather than a maximum? Well, we can use either the first or second derivative tests. Here, if we use, again, say the first derivative test, or well, just to illustrate, let me maybe use the second derivative test. So I could say the second derivative of surface area as a double prime would be equal to 4 plus 216 x to the negative third, or division by x cubed. So at x equals 3, clearly this value is positive, which means that my function is concave upward at that critical value. So that critical value must yield a minimum rather than a maximum. Our last part of the problem is to answer the question in the way that it was worded. We were asked for the dimensions of the box, which give the minimum amount of material. So we need the length, width, and the height. So far, all we have found is the width, x. So here, our dimensions would be x equals 3 for our width. Now the length we were told was twice the width, so 3 by 6 for twice the width. And then our height was what we called y. Now here, y had to be 18 divided by x squared. And so if x is 3, we have 18 divided by 9, or 2. So our dimensions would be 3 by 6 by 2. Everything was measured in feet, so we would have cubic feet for the volume of that box. All right. So let's consider another one. So the following problem, sort of a classic problem for optimization. So here we are given a rectangular field which is to be enclosed on all 4 sides with the fence. And fencing material costs $3 per foot for 2 opposite sides and $6 per foot for the other 2 sides. So we want to find the maximum area that can be enclosed for a cost of $2,400. So again, let's visualize our problem. We're enclosing a rectangular field on all 4 sides with fencing. And we're told that fencing material costs $3 per foot for 2 opposite sides and $6 for the other 2 sides. So we know that our parallel sides have to have the same length. Let's call them x and y. And so we are trying to find the maximum area. So the function that we're trying to optimize is area, let's call it a, which for a rectangle would be x times y. Now here our function again is a function of 2 variables, both x and y, and we only know how to optimize functions of a single variable. So we need to use some more information to reduce this function to a single variable. So let's use the information that we're given about the cost. So we have $3 per foot for 2 of the opposite sides. So the way I've drawn it, probably the longer sides would have the cheaper cost if we're trying to minimize our cost. So let's say our cost would be, well, for the cost of the 2 sides of length y, the longer sides would have the cheaper cost. So we have 2 sides of length y, and those would each be $3 per foot. And then we have 2 sides of length x, and for the shorter sides we might use the more expensive material, which is $6 per foot. So we would have 2 sides of length x times a cost of $6 per foot, and we're told that this cost would be $2,400. So we have 2,400 is equal to 6y plus 12x. So solving for y in terms of x, we would have 2,400 minus 12x is 6y. So to get y, we could divide both sides by 6, and we would have, let's see, 2,400 divided by 6 would be 400 minus a 2x. So substituting that expression for y into our area function, we have the area would be x times 400 minus 2x. Or simplifying, our area function is 400x minus 2 times x squared. All right. So in order to maximize this area, we would look for critical values. So taking the derivative of our area function, we have 400 minus 4 times x. And to find critical values, we set this derivative equal to 0. So here, 400 is equal to 4x, and therefore x is 100. So now, how do we know that this value yields a maximum area, not a minimum? Well, we could use the second derivative test. So looking at the second derivative of our area function, we have negative 4, which is certainly negative or less than 0, which means our function is concave downward at that critical value. So that critical value must yield a maximum rather than a minimum. Let's finish out our problem by answering the question in the way that it was asked. We're told to find the maximum area that could be enclosed. Now we know that to get the maximum area, x has to be 100. So we need our y value still. So if x is equal to 100, then the other length, y, is equal to 400 minus 2x. So 400 minus 2 times 100 is 200. So the maximum area would be a equals x times y. So 100 times 200 would give us 20,000 square feet.